I'd now like to welcome Professor Ian Megson, who's the head of Health Research and Innovation within the University of the Highlands and Islands, to introduce our new professor. Ian.
Thank you, Sandra. It's a huge honour and pleasure to introduce our speaker today, Professor Alistair Kean. Alistair joined us a few years ago, and we were hoping and praying that we would have an opportunity to do this inaugural lecture in person, but unfortunately events have turned against us, and we did eventually give in to the online version. However, I am absolutely certain that Alistair's going to produce a fascinating talk. He always does. He and I have shared a glass or two of beer discussing the wonders of physics, and I really think this should be a fascinating discussion. But it's my duty really to introduce Alistair and to give you some background to how he came to be with the University of Highlands and Islands. Alistair studied applied physics at the University of Strathclyde, and he followed this up with a PhD at the University of St Andrews, where he was working on dye quenching in organic crystals, so absolutely nothing to do with health. He claims he once scored an 82 at the Old Course Old Course in St Andrews, and he also claims he has the 18th flag in his home office. So if anyone from St Andrews is here and is looking for that flag, we now know where it is. From St Andrews, Alistair moved on to both Cambridge and Glasgow. This was between 1987 and 1992. He was a research fellow at the Cavendish laboratories at Cambridge University, and he shared offices with several Nobel Prize winners, which is a real claim to fame. And following that, he moved on to the University of Glasgow to work on molecular beam epitaxy for optoelectronic semiconductor devices, easy for you to say. He was also a lecturer there for a year, but he decided to leave academia to experience industry. So I'm delighted that we've managed to convince him to come back to academia, albeit with industry, as you'll hear later on. In 1992, Alistair joined the Juno project, and at this point, he applied to become a cosmonaut. Not many people have that on their CV. So he saw an advert for it to become a cosmonaut in the paper, and he applied for it, and he got shortlisted to 16 from 15,000 applicants. He refused to sign a contract because there was no insurance. So probably a good decision from you there, Alistair. And again, we're delighted that you made that decision. Otherwise, you may not have come to join us in the end. After the Juno project, Alistair joined Sharp Laboratories of Europe from 1992 to 2000. So this was a step in a different direction from most academics, in that he joined a large multinational company in Sharp. And there he was helping to develop LEDs and lasers for DVDs and data storage, which of course have become a mainstay for all of us. Not satisfied with one company, he moved on from Sharp Laboratories to a company called Chameleon in the year 2000. He was there for 4 years. And then, once again, Alistair took a rather unusual step in that he left industry in that sense and went to see whether he could cook. So he joined an inn, the Mole Inn, and he cooked in that kitchen for a number of years as well. However, industry and physics and the excitement that comes with science enticed Alistair back in 2004, and he joined a company called Mantis Deposition in 2004, and he was there for 9 years. And this is probably where Alistair really got interested in nanomaterials and nano deposition onto surfaces, which of course is key to his current role with the university in nanotechnology. Mantis went bust, which is what companies sometimes do, and this is a point where Alistair took a plunge into the unknown and decided to start his own company. And Nanoworks was the result of that move to form his own company. Alistair still is a director at Nanoworks, and we obviously hope that there will be collaborations between not only Nanoworks that Alistair is involved with directly, but all the companies that Alistair has come to collaborate with through his industrial contacts. One of those is Johnson Matthey, which is a large mineral mining company that Alistair is currently consulting with. So his time with UHI is part-time, but we're delighted to share his time with the likes of Johnson Matthey, because again, it gives us that collaborative opportunity. Alistair was working with Nicolite when he came up to Inverness in 2016 to discuss a collaborative project that we were putting together with a company that he works closely with around antimicrobial coatings for medical devices and for use in hospitals. And it was then that I met Alistair, and we obviously hit it off straight away and had lots to discuss about what we thought was the exciting project that is CityDeal at the University of Highlands and Islands, and which extends across the whole of the region. CityDeal is a £9 million project from the UHI perspective, and the concept was to bring into the university that collaborative aspect with industry, and Alistair just seemed the perfect fit for that post. Equally, we wanted a really novel and exciting angle to bring to the university and to attract companies to the campus in Inverness, and medical nanotechnology really hit the spot for us. We felt there was extraordinary opportunity there, and you know, the chance to put UHI right up with the very best in terms of novel techniques to challenge the paradigm that we have in medicine, particularly around medical devices. So I'm delighted to say that we managed to convince Alistair that it was a great idea to move here. I say move, of course, unfortunately, COVID-19 has come in and affected his ability to actually be in Inverness as much as he would like to be. And he certainly always loves his time when he comes up here. And as I say, we would have loved him to have done this presentation in person, because his enthusiasm, as you will find out in a few minutes, is infectious, and in person he just has the ability to capture the imagination of all of his audience. So without further ado, I'm going to hand over to Alistair, and please remember to put your questions in the Q&A aspect of WebEx, and we'll come to those at the end. Alistair, over to you.
Ian, thank you so much for that introduction. That was a very kind introduction. And yes, you're right about the point about academia. I vowed once that when I was in industry that I would never move back into an academic position. And throughout this discussion, we'll find out why UHI is so unique and why I was drawn back to such a unique academic position. So today, first of all, thanks very much to Jill McNichol for organising this meeting and hosting it and putting us all to rights. Thank you for Sandra for introducing the talk, and thank you very much to Ian for his introduction to the day. As Ian said, it's a great shame it's not in person, because what I've missed over the past couple of years is, especially up in Inverness, is bumping into people and having a coffee and having a chat, because that's really where innovation happens. It's a great shame it's not in person, but I'm happy to say, you know, it's a time when an inaugural lecture where you share things with your academic partners and colleagues and also family. And I'd love to have been up in Inverness with my family and, you know, just enjoying the social life and the great ambience in Inverness. My family are spread all over the place, but I've been poking a lot of them to join us. So hopefully I've got my son Finley, who's just started up at Durham University. My wife Diana, who's probably working in a nursery now, said she'd try and join in. My daughter Isla, it's her second anniversary with her boyfriend, so she said, I'm not going to listen to you, Dad. And my wife is American, so I'm hoping that I've got my family over in Maryland, southern Maryland, listening in to, so hi to the Ulrichs on the other side of the Atlantic. And at this point, a special thanks to Ian Megson and Jeff Howarth, who was Vice Principal of Research and Enterprise at the university. It's down to Ian and Jeff for persuading me, encouraging me to think about a post back in academia. So thanks very much, Ian. And the reason I took the post at UHI is I've had opportunities for the past 20 years to move out of industry back into academia. You have to visit UHI to see why I came, but UHI is such a unique place. It's up in Inverness, but it's spread all through the Highlands and Islands. It's an incredibly unique university. It's a young university, and therefore there is quite a blank canvas. It's a small university, which has advantages and disadvantages, but one of the huge advantages is that we all talk to each other and we can make things happen very quickly. So I'm really excited about what's going to happen there over the next few years, coming years, especially on the Inverness campus, which is a 250-acre site that we're developing. So without further ado, I shall attempt to share my presentation. And hopefully, if you can all see that, perhaps someone could interject and tell me that they can see the presentation.
We can see it, Alistair, but it's the other format, so I don't know.
Okay, I'll try a different method. How does that look, Sandra or Jill?
Perfect.
Lovely, okay. So I'm going to talk for about 25, 30 minutes. We're not going to get too technical here, but as Ian said, you know, I'm fascinated by most things, especially science. My background's in physics. I've worked a lot in physics, as Ian mentioned. With Johnson Matthey, I'm working in nanotechnology and chemistry, so learning a lot about chemistry. But what's absolutely fascinating me about my work in Inverness is applying my knowledge in physics, chemistry, limited knowledge in biological systems to healthcare. So essentially using physics, material science to interact with the extremely active research area that Ian already has had active for over 10 years up in Inverness. One thing I'm especially interested in is nanotechnology and how we can take take lessons from nature. So in this presentation, I'm just going to give some examples of what nature does and how nature operates and how we can relate that to nanotechnology. After that, what I'd like to do is give you some examples of where we can see nanotechnology around us. And then we'll look at some examples of how we can potentially apply nanotechnology, nanomaterials to healthcare solutions by finishing up with some specific examples. So we'll start off with something extremely simple, but in many ways extremely complex. So this is a beautiful photograph I took in June actually this year over in a forest just outside of Ullapool. I think when most people go into the forest, especially my children, they'll go into the forest and say, is it lunchtime yet? When do we get there? What's for dinner? Can I go back and play in my Xbox, etc.? And they'll often wonder why I'm just kind of wandering about looking at things. And I just caught this vision of a forest, and you look up into the sky, and there's some clouds you can see in the distance, which are water vapor, which interact with light in some amazing ways. A blue sky, it's blue because of a phenomena called Rayleigh scattering of light. And then you just look a bit at the green leaves and the trees. And for me, I look at the leaves and think, well, why are they green? That means they're absorbing other wavelengths. What are they doing with those wavelengths? How do they live? How do they absorb photons? And the trees are also made up of wood. And wood, I won't go into details in this lecture, but there's a material called nanocrystalline cellulose, which is refined from wood, which will be a wonder material of the future, allowing things such as plastic, concrete, windows, biomedical devices, which are completely biocompatible and biodegradable, so incredibly good for the environment. So this is the world according to Alistair. I'm a great admirer of Alexander von Humboldt, who was principally a naturalist. He was kind of the inspiration for Darwin to set off on his voyages. But prior to Darwin, Humboldt explored the world and looked at the beauty of nature. At one point, he was the world's most experienced mountaineer, climbing peaks in South America to look for vegetation and insects and try and figure out how the world worked. But one of the things he said, which really resonates with me, is that our imagination is struck by what is great, looking out the world. But anyone that loves the natural philosophies should reflect equally on the little things. So I think if Alexander was around these days, who knows, I might be working with him on the small things. I've taken this picture, we're just looking at some leaves there, water droplets on leaves, and how the water interacts with the leaves, how the leaf is hydrophobic. It keeps water away, but also absorbs water. And then water itself, how it interacts with media is fascinating. So I guess when Alexander was doing his examination of the small things, he was looking at things on probably about the millimeter scale. So during this lecture, we're going to get a million times smaller and see what happens. People often ask me about physics and they say, what's physics? And I've got a very simple answer to physics. Physics is the study of energy and the applications of energy, and that's it. That's physics in a nutshell. You can extrapolate and say that involves things like electromagnetics and photons and electrons, but they're all energetic. Also, people ask me about nanotechnology. What on earth is nanotechnology? We'll get to more specific definitions of nanotechnology in a minute, but first of all, let's look at nature. So when people ask me, yeah, Alistair, what is nanotechnology? I'll just ask them to look outside, describe what they see, and quite often you can describe that in terms of its operation at the scale of nanotechnology. And what we find is that a lot of nature, life sciences, biology, physics, chemistry operate at the nanoscale. We'll go into the definition of what is the nanoscale later on, but just as an example, this is a beautiful butterfly, which I photographed in a garden in southern Maryland earlier on this summer. Thankfully, I was allowed into America because I'm married to an American, just in case any of you are asking how I got there. If you take a butterfly wing and put it into an electron microscope, you'll see on the bottom right-hand slide here an image. So this is a structure on the surface of a butterfly wing. In physics, we describe this kind of material as a metamaterial. And essentially that is a metamaterial is a structured functional material. The structure of this butterfly wing allows it to absorb and reflect light with incredible control. So the butterfly we see here is orange in color. If you look at the actual material of the butterfly wing, it's actually quite gray in color. The reason it's orange is because it has a nanostructured wing, which specifically interacts with light to absorb and reflect. And that's a nanostructure. That's a beautiful example of a natural nanostructure. What we try and do in nanotechnology is replicate what nature has done in many ways. The advantage nature has had is that it has had many millions of years to evolve, as Darwin would say, evolve over the years to protect its own species by evolving in the way that is most efficacious for its own species. That's quite fascinating. Another great example in nature is this little chap here. This is the Namib, the Namibian desert beetle. So this beetle survives in some of the harshest environments on Earth, in deserts where there is no water, virtually no water vapor in the atmosphere. But if you look at its back, you can see that there are droplets. If we look at this beetle in more detail in an electron microscope, you can see at the nanoscale, it is a periodic structure of hydrophilic parts that attract water, and hydrophobic parts. The way the beetle survives is that it attracts water molecules to its surface. When the water droplet is of a specific size, it moves to a hydrophilic channel, and these channels direct the water droplets into the mouth of the beetle. It's absolutely fascinating. This technology has actually been taken up, and there's a technique called nano imprinting used to mimic this kind of coating, so that British soldiers now have tent fabric which mimics this beetle, so they can take tents into the desert and waking up in the morning with a cup of fresh water at the base of their tent. So that's a real application of mimicking nature using nanotechnology. My American family might recognize the image on the right here. We had a lovely day out at a farmer's market in southern Maryland. Thank you to Pete for taking us. But again, it's nature. On the left-hand side, we have the latest super mega nanomaterial in which the colleagues at the University of Manchester gained a Nobel Prize some years ago. So Manchester is a hotbed of graphene research, which is a two-dimensional nanomaterial. But if we look in nature, you just see these kind of structures replicated all over the place. So on the right-hand side, we have a beautiful honeycomb with one of the combs with a little bit of honey left in it. So again, just let's look to nature. Nature does it best. Let's try and mimic nature a bit and use our advanced technology to try and do some good. So in order to explain a little bit about nanotechnology, I think I'd like to step back about 50 years to the beginnings of what we call microtechnology. So microtechnology is working at the scale of a micron. So we can always relate to 1 meter in size. If we divide a meter by 1,000, we get 1 millimeter. If we divide a meter by 1 million, we get 1 micron. So 1 micron is really pretty much impossible to see by the eye. It's possible to see about 100 microns by your eye. And to envisage what 100 microns is, if you pluck one of the hairs in your head, then the width of your hair is around about 100 microns. So it's pretty small. But if we go back to the 1970s and look at transistors and microelectronics, one thing to say about microelectronics is it's quite obviously the greatest technological advance ever by humankind. And the reason for that is if we look at the graph and follow that graph, trying to put a pointer on, hopefully you can see that, but follow that graph up and look at the logarithmic scale on the left, you can see the increase in the amount of transistors per unit area from 1970 pretty much up to the present. So we've gone in the 1970s from about 1,000 per unit area up to about 50,000 million, which is unbelievable. I've got a picture here of my calculator, which I still use, which I bought in the late 1970s, and it fits probably in about here. It has about 1 kilobyte of memory, and I upgraded it to 2 kilobytes. But to think how things have advanced since then is quite astonishing. Where we are in 2020, microtechnology, microelectronics is now at the nanoscale. So the size of transistors is a tiny fraction of a micron. We have to go down, divide microns by another factor of 1,000 to get something called a nanometer, which is a meter divided by 1,000, then 1,000, then 1,000, or multiplied by 10 to the minus 9. So that's taken us up to pretty much the present day. Microelectronics, nanoelectronics is a kind of nanotechnology, but it's a very planar technology in semiconductor technology. So let's move on to nanotechnology now. So what is nanotechnology? I've looked at the US, the European definitions of nanotechnology, and I put together words in a way that I find it most easy to understand. So my definition is nanotechnology is science, engineering, and technology conducted at a size of 100 nanometer or less. So that means that we've gone from the millimeter to the micron. 100 nanometers is 1/10 of 1 micron. Anything less than that, we can class as being a nanotechnology. It's the science and engineering of, now we know, extremely small things, and nanotechnology can apply to pretty much any area of technology. In fact, nanotechnology was alluded to by Richard Feynman, famous American physicist, in 1959, actually, where he challenged an audience at Caltech to really go for it and look at materials, really analyze them, try and work with them, take them apart, and go down as close as you can to the atomic scale and try and do something with them. In 1959, that was a very, very big challenge. But towards the 1960s and 1970s, technology advanced so that we could start to think and manipulate material at that kind of scale. And that's when the term nanotechnology was first used. Here's some pictures of mine, which again illustrate what things are like at the nanoscale. As we've explained earlier, we take a millimeter, we divide the millimeter by 1,000 to micron by 1,000,000, we get down to 1 nanometer. A nanometer is probably, if you think of atoms, atoms are again smaller than nanotechnology, but 1 nanometer buys you about 3 atoms of building block material. So we're just above the atomic scale. On the left-hand side here, we have a very nice image of nanoparticles. These are less than 100 nanometer. And then if we zoom into these nanoparticles, technology is so amazing now that the blue circle is 1 nanoparticle, and we can actually image individual atoms within this nanoparticle. So this image was taken by a Johnson Matthey colleague of mine at the Diamond Light Source facility in the Rutherford Appleton site, which is where we have an incredibly sensitive microscope, so we can actually see the representation of atoms and the space between them. And we've seen the butterfly that we've described in previous slides. So why nanotechnology in life sciences and healthcare? Well, let's just focus on this vertical bar scale at the center. And for the sake of time, let's just focus on the scale 100 nanometers to 1 nanometer, which we've described as being in the nanoscale. And what you find in the nanoscale is that certainly in life sciences, we're at the scale of small molecules, and up at the larger scale, surprise, surprise, we're at the scale of viruses. So as we'll see later on, a virus or a virion particle is actually a nanoparticle. And that's fascinating to us because we're operating at the nanoscale, and nature and disease operates exactly at that scale. So we have to operate at that scale to interact with such materials in the future. Now, quite surprisingly, nanotechnology has been synthetically driven and used for hundreds of years. So the top left-hand picture here is a blade that was made many hundreds of years ago using a special technique. The steel itself is called Damascus steel. It holds an incredibly sharp blade, and it's only recently that we've had high-resolution microscopy where we've been able to take a slice of one of these blades and zoom in. And if you see in this image, we have got dark lines in this image, and that's right at the edge of one of these blades. The dark lines in this image are actually a structure called carbon nanotubes, which were developed synthetically only a few years ago, but by fluke of nature and the Damascus steel process, because of the lamination and tempering technique, naturally forms carbon nanotubes at the edge of the blade to keep it sharp. So they were being extremely clever, but they didn't really know it. On the right-hand side, we've got a lovely stained glass window, which is not 100 meters from where I'm sitting just now in Oxfordshire. And stained glass is another example of nanotechnology. To make blue stained glass many hundreds of years ago, the engineers, technicians would take glass, melt it, and they would dig up some silver or mix it in with the glass, and the glass would turn blue. Unbeknownst to them, they were generating silver nanoparticles, which have a nanoplasmonic optical effect in the stained glass window. So I've had many interesting conversations with our local minister about such effects. So nanotechnology is out there. How do we use it? First of all, nanotechnology can be applied to so many different things. Just to whiz through some areas here, people are looking at textiles, biomedical we'll talk about, and healthcare, also food and agriculture, industrial, so I'm working on catalysis with Johnson Matthey, electronics, there's the quantum revolution, which is being enabled by nanotechnology. Also close to my heart and important in the future is how do we manage air and water environment in the future using nanotechnology to detect pollutants, to filter things, to make things safe. Also renewable energies, so for harvesting energy from sunlight, nanotechnology is playing a large role. So there are just so many areas in there. What does a nanomaterial look like? So on the top left here, we have a piece of filter paper, and using the technologies I use now and will be using in Inverness, we can apply a gold coating to surfaces quite easily. So if we do that, because it's in filter paper, it's a kind of browny gold coating, but that's a thin film of gold on a filter paper. If we take that gold and not use atoms to deposit and make a metal film, we change those gold atoms into nanoparticles and make a nanostructured nanoparticle coating. And that's the coating we see on the right-hand side here. So on the very right-hand side of this filter paper, we see a dark grey coating, which is exactly the same loading as the gold on the left-hand side. It looks grey because it's not normal gold, it's a nanostructured gold, which has completely different properties to bulk gold. If we move over to the left, you can see there's a slight pinkish tinge to that, and that's going back to the stained glass window, where silver gives us a bluish tint, gold gives us a reddish tint, a pinkish tint, because of the nano properties of that material. And again, here's our nanoparticles zooming into one nanoparticle. The little dots you can see in there are individual atoms. So the ability to control at such scale is absolutely phenomenal. Zooming in, as we did even earlier, we can look at these two nanoparticles, the atoms in them, and to give you an idea of the scale we're working at, the orange bar separates two merged nanoparticles. This line that separates the two nanoparticles is about 4.2 nanometers in length. If we use this scale, and this orange line, which might be about 10 or 20 centimeters on your screen, as represented as 4.2 nanometers, at the same scale, if we placed a human hair beside this orange bar, the width of the human hair would be about 2 kilometers. So that's the scale that we're working at. It's almost unimaginably small, but that's where things happen. So we've seen that nanotechnology can be applied to many different areas. If we look at how nanotechnology can be applied to medicine, healthcare, biochemistry, there are areas such as imaging, where we can look at things, delivery of medicine, nanoreactors, so there's more than a lifetime work for more than one persons in all of this. Up in Inverness, we're going to zoom into a little bit of this area. We're going to start organic nanoparticles as time goes on for various applications. But we'll be certainly looking at imaging, spectroscopy, and such applications in Inverness. At this point, I thought it'd be interesting to mention nanobots, because people are worried about nanobots, the possibility of self-generating nanobots that can move around the world, self-replicate, and trouble us. So I think we need to just look at this a little bit more logically. So this image we have is a kind of artistic representation of what a nanobot might look like. But the physicist in me looks at that nanobot and says, oh, hang on a minute here. In order to make a nanobot with arms and legs and controllers and vision, that's quite tricky. So if we look in this nanobot, we have a CPU, so we got a computer chip controlling it. It's got arms to control things. It's got optics. So I can look at this and say, I don't think that's going to be very small, that beast. I don't think it's going to be a nanobot. So I did some thinking. So maybe you can imagine how large in reality that nanobot might be. I looked at it and I figured it's probably going to be about 5 centimeters in size. I mean, the whole thing is, if you want something to run using a processor, that limits the size. Also, optics, the wavelength of light is about 1 micron. That's not nanoscale. And also tribology. Tribology is how arms and legs move and wear. When you go down to the nanoscale, tribology falls apart, and it's impossible to make things move without falling apart at such small scales. So I think we need to take a step back and look logically. The logical argument for nanobots is much more akin to this kind of thing we see. Nanobots in the near future are much more likely to look like this kind of structure. So it's going to be a synthetic molecular structure designed with some kind of function. So it's not a nanobot with arms and legs, but it's more like a super molecule with structure designed for specific applications. And then we'll evolve these for therapies and various other applications. And again, it's very worthwhile noting that a virus is a nanobot in itself. It's a nanobot that we don't want. It's a nanobot that we want to detect and control. And that's what we will do with our coordination between our work in new nanotechnology and Ian's research and his fantastic colleagues in his department. So I'm going to talk about two specific examples before I finish up. One is an area that's fascinating to me that I've been working in for many years and bringing all my partners to Inverness to explore, is the potential to make antiviral and antimicrobial surfaces. Nature does this naturally. Insects have natural antimicrobial, antiviral surfaces. So I've been investigating how we might synthetically produce such structures. So I've been working with a company, Ginko Limited in Liverpool. We're looking at infections people pick up in hospitals. Even throughout the pandemic, infections in hospitals haven't gone away. They're still a huge concern. So we need to battle what we do with viruses. We also need to work very hard to stop people getting infected when they're actually in hospital. People pick up infections from things like touching handles and wiping their face. So how do we make these structures? We use a technique called physical vapor deposition. It's basically physics, electricity, plasma, and we use these techniques to evaporate materials, condense them onto surfaces in a controlled fashion to make our functional nanostructure. We've developed, ordinarily, in semiconductor physics, I would be making atomically smooth surfaces for a specific function. But what we discovered is if we want to try and mimic nature and make surfaces which bugs don't like sitting on, we have to start moving into the 3 dimensions and making nanostructures. So we after many years of research, we came across a structure which kills bugs and destroys viruses extremely efficiently by building up a nanostructured surface, and again, mimicking nature very closely. What about viruses? We see here that SARS-CoV-2, this is a very nice study done in the New England Journal of Medicine, and we see that viruses can sit on surfaces. Over on the right-hand side here, we have a nice example of plastic and SARS-CoV-2 virus sitting on that surface for several days and still being active. So we really need to think about not only viruses being airborne, but landing on surfaces and people picking them up. This is looking at copper. This is some really nice work carried out by a colleague, Bill Keevil at Southampton University. Copper is a natural antimicrobial, antiviral material. And these little round nodules are actual virions or virus nanoparticles. And he observed that by sitting on copper, the virus particles were quite actively destroyed. That's really interesting. But going forward, we can't make everything out of copper. It just wouldn't be economical or technically viable. So what we've tried to do is replicate the kind of effectiveness of copper by using our nanosurface. So to test how active our material is, we essentially try and populate a dish with cells and with viruses. If the virus is successful, then you're going to start populating your cells with the virus, and the cells will be destroyed while the virus replicates, and you'll see the cell count diminishing. What we then do is we apply our nanosurface to this kind of environment, and what we see is the reverse. We see that very quickly we get a very large kill or destroy rate of virus particles on that surface. So that's extremely exciting. Very exciting is that typically in a healthcare environment, you would see stainless steel all over the place. So it's very interesting to note that stainless steel is not antimicrobial or antiviral. So if we have a bug sitting on stainless steel, there's a high chance that it will be transmitted. So what we are trying to do with our technology is generate coatings which are antimicrobial, antiviral, but also extremely hard. At the nanoscale, it looks very rough, but at the optical scale, it's actually quite a very smooth finish. But it's rough enough at the nanoscale interaction with nature so that we kill bugs. You should always keep cleaning, and there's a whole area around biofilm formation that will be another part of our research. So to bring you up to speed, this is a very recent development where we have taken orthopedic implants. On the left-hand side, we have a stainless steel implant, also a stainless steel surgical instrument, which we now know will happily host bugs and viruses. On the right-hand side, we have our nano-coated orthopedic implant and surgical instrument. The surgical instrument is going back to Surgical Holdings, a UK manufacturer, and the orthopedic implant is going back to partners in Brazil for further testing. So that's extremely exciting, the potential to reduce the possibility of infection. Another theme is how can we use nanotechnology to detect bugs? I can see that I've been going on for about 35 minutes or so, so I'm just going to whiz through the slides and then finish up. But I thought it'd be interesting to move to an image of a technique that we're using. So to detect bugs, we're using a technique called Raman spectroscopy, which is a way of using photons to detect chemical signatures. Raman spectroscopy is very inefficient. About 1 photon in a million gives you a scattering event that gives you the information that you're looking for. By using our nanometallic surfaces, these can act as a nanophotonic amplifier and amplify our signal by many orders of magnitude. And to do that, we've gone back to our gold. In the background, we've got gold coating on medical contacts. In our Petri dish here, we have a substrate coated with our plasmonic gold nanoparticles. And this substrate acts as a nano antenna to amplify the Raman signal. And when we apply our nanotechnology to this form of spectroscopy, we start to see spectra. This is a spectra where we're measuring fingerprints of molecules. But the important thing to note is that we are measuring a molecule down at parts per billion concentration. And some researchers are taking this as far as being able to do spectroscopy on individual molecules, which is quite revolutionary. So the possibility of using such systems to identify explosives, narcotics, medicines at ultra low levels is extremely exciting. How do we apply that to bugs and viruses? Well, what we'll do is take bugs and viruses apart and look for things called biomarkers. So fingerprints are indicators that these molecules exist. And I'm happy to say that Census in Glasgow, University of Glasgow, has funded a project between partners. So we actually have an active grant running now where we're developing sensors to detect pathogens in hospitals, which is very exciting. And the nice thing is we've got partners in here. We've got a really good partnership involving industry and academia. We have ourselves in Inverness, University of Strathclyde, Polycat Septium Pinpoint Nicolite. So that's a great collaboration, and the outcome of this project will hopefully be commercial application of this technology. So nanotechnology now and in the future, so many things are going to happen over the next years, decades and century. It's very exciting. Presently, we're looking at very basic forms of nanomaterials, but these are going to evolve into more active nanomaterials, doing some functional biochemistry with nanomaterials. We will be putting together synthetic nanomolecules and devices, and that will be the beginning of the revolution of biorobotics, artificial tissue, and then in vivo bioelectronics and computing. We're going to diverge from the earlier view of a nanobot. We'll do things following nature as a guide and trying to do good. We'll look for the good thing with an eye to bad things that could happen so that we can keep all of that under control. And that's where my work together with Ian will be extremely exciting in the future. So I've talked on long enough. It's wonderful to think of what we'll do in the future in Inverness. Thanks for listening in. Thanks to our collaborators in Inverness. Thanks to the City Region Deal, colleagues at HIE, HI and NHS. Work's going to continue up in Inverness, and we'll be moving into a new building on the beautiful Inverness campus in about a year's time in 2022. Thank you very much. Over to you, Ian.
Alistair, that was absolutely wonderful, as expected. Fascinating talk, and thank you very much for giving us your time to explain what is a really quite tricky topic for us mortals, and trying to explain the sizes or the extremities that you extend science to is really quite tricky, and I think you did it in a fabulous fashion. We have a question from Kate McDonald. Hi, Kate. Lovely to see you here. Kate asks, how easy is it to add an antimicrobial coating in situ to, say, stainless steel rather than on new small instruments?
Yeah, because I've been in industry, I never do anything unless I know that it's scalable. So the company I work with, Ginko, their research is new technologies and techniques for producing materials, but they also work with companies such as Samsung and Apple to productionize. So Ginko have lines in various big companies for producing coatings. So if we're looking at coating either tens of thousands of surgical instruments or large area coatings, then yes, certainly we have technology to do that. And my intention is that we will have active academic research in the next version of antimicrobial coatings at UHI. But we'll also have a commercial hat on where we will look to productionize this through a commercial output. And the form of that commercial enterprise will depend on customers we work with. So it may well be an orthopedic implant company, or it may be a railway company making ticket machines where they want to have antimicrobial touch surfaces for ticket machines, which is an active project that we have running just now. So I don't know if that answers it, but happy to answer further.
I'm sure that does, Alistair. But Kate is a fellow physicist, so you've obviously sparked her imagination. So she's got another question in there saying, at what stage in size do quantum mechanics effects come into play? Someone had to ask about quantum mechanics. This is way over my head, so over to you, Alistair.
I paid her £100 to ask me that question.
I know you did.
No, I didn't. I just didn't have time to get into it. But quantum mechanics. So really, quantum mechanics in material systems really starts to kick in when you get down to about 10 nanometers. But quantum mechanics happens all over the place. Talk to James Cobley about it. Quantum mechanics takes place in life sciences and biomolecules. It's just very hard to see in everyday life. The phone you have in your hand operates on quantum mechanic principles. So in nanotechnology, there are nanotechnology building blocks which operate in the classical domain. So you have classical physics and quantum physics. Classical physics is determined by things like Newtonian mechanics and Maxwell's laws. The plasmonic absorption we're seeing is actually classical Maxwell equation, classical physics. But when you go down to small structures, then you can have things like quantum, a phenomena called quantum mechanical tunneling between adjacent nanostructures. So I'd be happy to set up another inaugural lecture to discuss in more detail. But it's a very good question. Nanotechnology and quantum mechanics are quite embroiled in each other.
Great, thanks. And Kate's come in with a third question, which is a tongue-in-cheek question, I think, saying, when can we hope to have a physics department at UHI? To which my answer instinctively is, we now do. It's just one part of physics and not the whole of it. And of course, biology invests in physics all the time. So I'm afraid, Kate, if you're wanting a full physics department, it's going to be some time, but we're doing our best at a very small scale.
Yeah, we have myself and Susanna, our postdoc, who's joined us and sort of co-supervising Manuel. So we're wedging in physics. Everyone needs physics, Ian.
So you keep telling me, yeah. Alistair, but when we discussed your vision of the future, and I apologize in advance for this sounding like an interview question, but you've always expanded on where you see your vision of UHI in the future going in terms of nanotechnology. Can you perhaps share some of those thoughts with the audience today?
Yeah, obviously, nanotechnology is such a huge area, and we can't do everything. One of the beauties of being at UHI in Inverness is that there are topics in Inverness such as life sciences and healthcare, but also environment, aquaculture, agriculture, water, air. So I'd really like to push into these areas. Because I've worked for many years in industry, I can bring my tendrils, which are out there, into industry. One huge part of our work will be, and we discussed this within the university, is funding. Funding from the government, whether it's Edinburgh or London, is becoming harder and harder to gain because there are so many people applying for it now. So my ambition is to build consortium involving academia, SMEs, new SMEs, large-scale companies. But it's almost like COVID has changed things. I think COVID has fundamentally changed the way we should work together. Rather than being competitive, we should look to the future and really try and work together to solve some of the world's problems. It's a rather large challenge, but that's my ambition, is to enhance nanotechnology. I want to see young people working in new enterprises in Inverness. I want to see cooperation, but more than anything else, I want to see Inverness recognised as a place to visit, a place for people to come and work and advance science and technology.
That's brilliant. Thank you, Alistair. I see that that Sandra has appeared on the screen for me, so I'm taking the hint that that's probably time to call the Q&A to an end. So I'll hand over to Sandra to close things off. Thanks very much.
Thank you, Ian. And can I add my thanks to Ian, to Alistair as well, for absolutely fascinating run through of the wide range of the applications of nanotechnology through the natural sciences, and then ending up, of course, with a very contemporary situation with opportunities for real impact in the areas of infection, something very close to my heart as a clinician. So Alistair, it's my duty to welcome you and say a little bit about the Professoriate, but a professorship is only awarded to highly accomplished academics. It's the highest rank in academia and a very privileged position to hold in serving both the university and the wider community. We in UHI have recently celebrated our 10-year anniversary and have over 50 professors in a wide range of academic disciplines, and we can now add this exciting new area of medical technology with our new Professor of Medical Technology. I'm sure that our new professor will a hugely rewarding experience. He's been with us for some time now, and he's already alluded to that in his new role. And in turn, that will significantly be enriched by the value of his input. And again, he's given us examples of what's been happening already. So please join me in welcoming Professor Alistair Kean to the Professoriate in the University of the Highlands and Islands, the Professor of Medical Nanotechnology. And can I just wind up by thanking all of you today for joining us. There will be a video, it will be available on YouTube in the next couple of weeks. Can I also invite you to the next event, which is in fact tomorrow, the 7th of October, and that will be given by Professor Ingrid Mainland, and that's entitled Of Trough and Trencher, Exploring Food, Fodder and Feasting in the Past and Present. And that's Professor Mainland's inaugural lecture tomorrow at 4 o'clock. Details of any further events, of course, you can find on the UHI website. So thank you all again. Thank you, Jill. Thank you, Ian. Thank you, Alistair. And thank you to all of you for joining us today. Martian Live.
Thanks very much.